So I'm going to try to make sure that I speak in English. It's happened before that I said, okay, well, this is an international conference, so I'll speak in English, and then I started speaking in French. It's not clear how this happens. So thank you, Nadia, and thank you, Francois, for the introduction, for the organization. It's really wonderful to be here. So it was determined earlier today that among all the former PhD students who were advised by René Carmona, I'm the most ancient in the room today. I got my PhD in 1996. Professor René left UC Irvine in 1995, so I felt completely abandoned. Right? But he talking about correlation today. Yeah, and so there's a negative correlation with that particular event because afterwards he certainly provided an enormous amount of support for me throughout the years and still to this day, and so I'm so eternally grateful. He's been a great mentor. I feel very fortunate to have had him as an advisor. Life really is stochastic. When I came to the UC Irvine PhD program in 1990, I didn't know anything about probability because I came from an environment where there was no option to learn probability where I went to school. I often explain that I don't have an undergraduate degree. This is true. I never went to undergraduate school. At the time, I don't have an undergraduate degree. At the time, I was going to, I used to be French. This is something which my wife says isn't true. She thinks I'm still French. I'm from California, but I was going to prépa in the late 1980s at the lycée Janson de Sailly in Paris. Anybody here ever went to prépa? I think maybe there are one or two people in the room. Yeah. Okay. Like some of you who actually did very well with prépa, unlike some of you, I didn't do well at all and decided that because I was raised by an American mother, I decided it was really time for me to not pretend to be French anymore and to leave and go back to the United States. Came to the Los Angeles area, which is where my mother lived. My brother had already left. He'd already started going to regular, true college. He has an undergraduate degree and I don't. And so life is stochastic. It turns out that Professor René, so I did everything wrong. I decided to apply for graduate school after only 2 years of college. It wasn't even college, it was prépa, so like try to explain that in American school application, it's just never going to happen. But René, I don't know if you remember this whole story, but yeah.
They were telling me this guy's from a high school.
Yeah, like how is this guy applying to grad school when his letters of recommendation are a high school teacher's? Like, who is this guy? Like, and then it turns out, and I don't remember the woman's name, but you were friends with the woman who was in the engineering school at UC Irvine, and her son went to the same prépa that I went to. And so I think you asked her, so do you think this prépa is any good? And she said, like, what? Of course it's good. And so life is stochastic. I didn't know any probability or stochastics or nothing at all. So thanks to this woman whose name I don't remember and I wish I did, she spoke with René. René actually had to ask the administration, you know, UC Irvine has improved a lot since when I was in grad school there, right? But back in those days, he had to explain to the administration, you told me 3 different times you had to insist and you had to get into fist fights with people. And after the 3rd time, they said, well, you're such an idiot, René. If you really want this kid, okay, you can have it, but he's going to be a disaster. Yeah, because he's a high school kid, right? So that's what happened. Life is stochastic. René got me into the PhD program at UC Irvine. You know, by the way, so this is how conflicts of interest used to be handled in the United States, not anymore. The person who was in charge of the graduate program at UC Irvine at the time when I was admitted was my freaking cousin. And even, yeah, my cousin, and even with Bernie. He's my cousin. Did you know that? Yeah. Yeah, I saw him not too long ago, like 2 months ago. Yeah, he's still my cousin. And even with my cousin in charge, René still had to put up a fight. And then, so René thought I was French, so did I. You know, so we kind of like, you know, had a connection that way. And then I realized, oh, probability? Really? What is that? Oh. And then René's like, this French kid is well trained. I'm going to see if I can maybe be his PhD advisor. And I'm like, really? Somebody wants me as a PhD student? Like after I had the, so it was just a wonderful experience. I became a probabilist just by accident in a stochastic way. And I'm really glad that I did. And yeah, I can't say enough good things about the way that René helped me get trained, let me do whatever I wanted. When I was a student, he like completely hands off. I just had these weird ideas about what constituted a PhD thesis. He let me do it anyway. And so thank you, René, for everything. Let's give him, yeah.
Remember the shoulder when we face
Oh, that was another story. So, okay, I don't know. I'm not going to get through these slides, but that's okay. Like this is maybe like 4 years into the, I stayed 6 years in the PhD program because I loved René so much. Yeah. And in my 4th year, we played soccer together. He was still coaching his. How long did you coach the soccer team for your children?
No, I didn't coach the soccer team, and I was playing in 2 teams. Yeah.
Oh, you're playing. Okay, yeah. Because he was also a marathon runner and everything else. You know, me as a Neanderthal, I'm an ambush predator. I really shouldn't be running anywhere. I just pounce on animals. I don't run. But back then, I thought I would run, and so we were playing soccer. And Statistician, who was the first PhD student who left Irvine to go to. So he was my I don't know if you guys know Statistician, but so Statistician, nobody knows Stas? Anyway, so I was pretty fast at the time, and Stas was like maybe like 1.5 feet taller than I am, you know, this wide, you know, Russian guy. And I was attacking, he was trying to defend, and he hit me with his shoulder, and I fell onto the ground, and with the speed, I broke my collarbone in half. And then René looked at, so he was poking out of out of my skin, and René looks at us, he says, "Oh putain." Yeah. And I'm like, oh shit, man. And then, who can take me to the hospital? And so everybody's like looking the other way, and René says, okay, I'll take you. Yeah. So yeah, there was that story. I was in a lot of pain for a couple weeks, but now, you know, I'm good. Yeah, that was a while ago. Okay, so that was another story. Anything else you want me to reveal? Okay, cool, all right. So thanks again, and yeah, thank you all very much for inviting me here. It's really an honor. So you can see the subtext of this is it possible to test the dependence of 2 random walks as they converge in lots of random motion paths? So my name is Frederi. I'm from the Department of Statistics at Rice University in Houston, Texas. And since I'm the most ancient PhD student supervised by René, you'll be able to notice that these slides are very low tech. They're so low tech that I don't even have René's name on the front slide. That's how low tech it is. And so, plan of the talk here, I'm going to talk a little bit about Yule's nonsense correlation. There's some mathematics involved here. In fact, in section 3, we're going to skip through this because there's so much math that people would run the other direction if we try to go through this. There's this notion of nonsense correlation. Raise your hand if you've ever had a statistics class, everybody. Not that many people are raising their hands, right? So how about the Pearson? Anybody heard of Pearson? Pearson correlation? Yeah, maybe? All right, okay. So we'll have a formula showing what Pearson's correlation is. When you have 2 time series and you try to see whether they're correlated, if the time series is represented by i.i.d. data, Pearson, and even before that, knew that you could take these 2, you compute the empirical correlation between the 2 sequences of i.i.d. data, and that's a very easy way to see whether those things might be correlated. You try to do that with other types of time series, and it may or may not work. When you use stationary time series, which are sufficiently stationary, the same effect happens as if the data were i.i.d. But if the if the time series are sufficiently highly correlated, just to say, imagine this, so I know this is a room full of statisticians, right? So maybe you can understand the Ornstein-Lombeck process, whereas if I talk about an AR1 process, you may not know that it's actually the same thing, right? So if you observe an OU process in discrete time, that's an AR1 process. AR1 processes, you can stick them into a formula for the Pearson correlation and expect to get the right answer if your 2 discretely observed OU processes are independent. The rho n will converge to 0 as the number of data points goes to infinity. This is a true fact. It's not a problem. It works really well. The OU process and the random walk are such different objects. I mean, we teach them in the same sort of way to students, right? But they're so different that if you try to do that same operation with random walks, you end up with a distribution which doesn't converge to 0. It actually converges in law to something which is completely diffuse. And that's what the topic of this presentation is today. So we'll go through a lot of that. We'll go through the second chaos representation of components of this rho n and find out what the limiting variance is. I'll show you very quickly a formula for the variance. This is joint work with Philip Ernst at Imperial College, and also Shuoyan, who's a postdoc there right now, and John Roberts, who's a PhD student at Rice. And here's who's funding some of this. And I'll probably go through the math very quickly because I also want to show a couple of pictures, one which has to do with work that I'm doing with farmers in northeast Nigeria. And the formula that I have on this board and the one that I was in the middle of writing on that one, which I'll have to rewrite, is I'm saying it's work in progress, but we already know the answers. We just have to finish writing things up on how you can use the asymptotic distribution of rho n's fluctuations in order to set up a positive answer to the question which was on the previous slide. So let's get going. So we were talking about time series. The letters S and T are maybe not that well chosen, but never mind. These are two time series. They're not necessarily independent. They're not necessarily stationary. We'll mostly discuss random walks in this talk. Those are not at all stationary. Like, you have to understand, how do we know that a random walk is not stationary? Because its variance increases over time. It's that simple. Am I right? Yeah. Okay. And here's the Pearson correlation that y'all said you didn't know about, but I'm sure that when you see it here, it's familiar. Am I right? Yep. This is familiar? Okay. All right. So this is your Pearson correlation for two time series of length n. To make our lives easier, we're just going to assume that the S and T, these two time series are identically distributed. The stuff that's down here is stuff I've already said. Most of this is stuff that I've already said. This idea up here is the fact that for a short memory stationary time series, rho n will converge to 0 if the correlation between S and T is 0. So for example, for the arrow-n process, or in continuous time. In fact, I have a paper with Soukaina Douissi that I'm going to go and visit tomorrow in Morocco. I'm leaving tomorrow for Morocco for another conference with Professor Soukaina Douissi from the University of, Qadi Ayad University in Marrakesh, and we have a paper on short memory or dynamic process, which is the same topic as this, but in continuous time. And in both of those cases, discrete or continuous, when you let time go to infinity, the rho n or the rho t goes to 0 for independent paths. But there's a statistician whose name was Udny Yule, and in fact, Yule was mentioned this morning in a different context. Yule did a lot of stuff. One of the things that Yule did was that he noted in 1926 this phenomenon that if you use two random walks instead of ordinary i.i.d. data, and you try to look at that correlation coefficient, which at the time was well known to converge to 0 if your i.i.d. data were coming from two separate independent things, he noted right away that it's complete nonsense. He called this phenomenon nonsense correlation. We still use the word today. It's in the title of the presentation. It's called Yule's nonsense correlation today. And the nonsense refers to the fact that it's nonsense to believe that rho n would converge to 0 when your two time series are very non-stationary. And in the original paper by Yule in 1926, he took, this was, y'all remember when cell phones came about? How about email? Anybody remember the time before email? How about the time before phones, before landlines? Yeah, remember that? So in 1926, that was the time before anything. And Udny Yule did the experiment by hand. I think he had like 600, he wrote down 600 sequences of 100 coin flips, and that's how he created his distribution of time series. And he counted, and he saw that indeed it's nonsense. And the distribution that he found looks a lot like what it really is that we know to be today. And so this phenomenon has been known since 1926. But since 1926, the variance of rho n, which converges to a non-zero number, so the law of rho n is diffuse over this entire interval, does not concentrate. There's no CLT. The variance of rho n converges to a specific number. If you think about what rho n does, here I have an exact formula for the limit in law of the entire sequence of the sequence rho n. So consider this expression here. Whoops. Consider two Brownian motions, two Wiener processes, W1 and W2. So one thing that bears keeping in mind is that we're talking about observing one Brownian path, W1, observing another Brownian path, W2. We're not sampling Brownian paths, right? So there's this notion that when you're trying to understand statistics, you can sample as many Brownian paths as you want and construct a statistic that way and then see whether you have independence that way, and that's an infinite dimensional problem. This is not what we're looking at here. This is just the question of two separate paths sampled once. One way that I try to explain this is that if you're working on environmental data, for instance, and you're trying to understand, so one of the applications, I'll show a picture in a minute, you're trying to understand the implications of the data that you're looking at, which is observed for planet Earth at a specific time or over time, and you try to understand what those empirical observations mean for you. We only have one planet. There is no planet B. So you're not running any experiments. Like, you can try to send up particles into the atmosphere to reduce the amount of solar radiation that comes to Earth through the concentration of greenhouse gases in the atmosphere. That's an experiment that you can run. You run that once, you'll probably destroy the planet. So that's your planet B. It's already gone. So there's only one planet, right? Everybody following the story there? Yeah. Okay. So we only have one planet, and we can make observations with it. And then you can look at a temperature time series. You can look at something else that might be related to your temperature time series. Those are your two time series. You look at those two things. Imagine those two things as two separate paths of Brownian motion. And you want to know whether you can attribute the phenomena that you observe for one to the other. Make sense? So we're talking about two separate time series. That's this W1 and W2. when you put W1 and W2 into this expression here, and then you create this random variable there, this is the limit in law of rho n. And I don't think I'll have time to explain all the details, but under certain circumstances, you can even show that this row right here is the limit of the previous rho n I had before when the relationship between the time series and the random walk is clear enough, which is the topic of my paper with Philip Ernst and our other co-author, who is at Colorado State right now. And why is it easy to see that this expression for this numerator here, you have I and j equals 1 and 2, and here it's this is 1, 1 and 2, 2. You look at this expression, why is it obvious that this expression should be the limit of the numerator? Well, if you remember what we had on the previous slide, this was the expression in the numerator for rho n. You stare at this for a second, and you realize that your sk is actually a sequence. Since it's a random walk, it's a sequence, it's a partial sum of i.i.d. Innovations here. So think of epsilon k as being coin flips, or think of epsilon k as just being any sequence of i.i.d. variables with any distribution that you want. In this talk, we're going to talk about the case where they're normal, but you can take coin flips if you want. Same thing with t, another sequence of coin flips. And I forgot to put sub k over here. Sorry, I missed the sub k over here. So sk and tk are just partial sums. So if they're partial sums, there's a CLT happening. We all know, yes?
Sn, I suppose, and Tn.
Ah, Sn and Tn. Merci, monsieur. Au moins, il y en a un qui fait quand même attention à ce qu'il y a au tableau, hein, heureusement. Hein. C'est parce que les autres, vraiment, là... Non, mais ça, c'est le côté français qui ressort, là. Ouais. Yeah, Sn and Tn would be what you obtain. When you have Sn and Tn down here and you apply the CLT, you're going to get normal limits. But if you look at it at the process level, Donsker's invariance principle tells you that you're going to get Brownian motions, right? We all know that, right? In this room, I've done this presentation before in a statistics department, and I explain this, and the people are like, what? And like, well, yeah, don't you guys have like a stochastic processes class that the PhD students have to take? And they're like, yeah, but what's Donsker? So, okay, I don't want to insult anybody. Well, I already have. Okay, great. All right, so Donsker tells us, yes, because of these two expressions and the way this is set up, the limit of the numerator here, which is this thing, should be exactly this expression. So I don't think that there's any mystery for the folks in this room. It's a very simple matter to show that rho n converges in distribution to rho just from Donsker's invariance principle. And then, but still, Yule asked, so clearly rho is diffuse because the distribution of rho is exactly the distribution of this random variable, so there's really nothing mysterious. However, nothing mysterious for people who understand Donsker's invariance principle. However, rho, which is diffuse, has statistics itself as a random variable. And Yule asked in 1926 if we could compute the asymptotic variance of rho n. In other words, can we compute the variance of rho? Can it be done? And so it's a mathematical statistics problem. It's not necessarily going to change the world if you figure out how to calculate it, but it's been an open problem. You know, how many people here have ever worked on an open problem in mathematics that doesn't have any bearing on the real world? Can you raise your hand? Come on, guys. I know you have. All right. Yeah, everybody's laughing. Nobody wants to raise their hand. I've done it. You know, thanks to Renee. I wasted a lot of time on that kind of stuff. So, do you remember magnetohydrodynamics, Renee? Magnetohydrodynamics? No, that was my PhD dissertation topic. I'm not saying I proved anything. I didn't prove anything there, but it's not necessarily going to change the world if we can compute the variance of rho. But Udny Yule asked in 1926 if we could compute the variance of rho, and that question was left open until 2017. So for 90 years. And Philip Ernst, who used to work the same place I work today at Rice, and now he works at Imperial College, he actually solved this problem, and he published a proof of the formula with two other co-authors. One of the two co-authors had died before he came out with the proof, so his former PhD advisor, Larry Shep. And the other co-author was a professor in statistics where Ernst was a PhD student at UPenn, but that professor wasn't a specialist of stochastic processes, so it's very clear where the proof came from. So when people say that Philip Ernst proved the formula, when people say that Philip Ernst computed the variance of rho by himself, even though there's two other co-authors on the paper, I think everybody agrees, everybody understands what the story is. Yes. Is there something? Okay, here we are. I'm so sorry. Like I said, I'm the most ancient former PhD student. René has better control over his small muscle coordination in his hand than I do. So, just one other little thing here, which I wanted to talk about real quick, and then we're going to skip over some other slides. If you take the same expression as we had for the numerator of rho and you rescale it this way, you will notice that, and you do the same thing to the two terms in the denominator here, you will notice that because of the scaling property of Brownian motion at the process level, the t's that you're using here are going to cancel out. So this expression here, which is the same, let me scroll back real quick. If you look at this expression here, I have a 1 in the upper end point of integration. If you look at this expression, it's the same thing except there's a capital T. But if you do the scaling, because this thing is a ratio, rho is a ratio, and all the t's cancel because of the scaling property. This is something which is totally obvious, but somehow it had never been written down, and so we finally wrote it down in this paper with Sukaina Duisi and Khalifas Bai. It appeared in EJS 2022. Interestingly, although we haven't really been able to do much progress on this, if you replace your Brownian motions by fractional Brownian motions or by any process which is self-similar, it doesn't even have to be, it could be any self-similar process, this exact same effect occurs. So when we're talking about what are the kinds of time series where the Yule nonsense correlation ends up happening, well, an answer is it happens for Brownian motion, it happens for any self-similar process. In the case of any self-similar process, you're going to have a Donsker invariance principle, like an infinite dimensional CLT, that's going to happen with your long memory time series, for instance, and the same effect will happen, and the limiting distribution will be the same expression. So that's also interesting. Therefore, there's no concentration. As t goes to infinity in the previous expression here, you see that it's not the place to look for a concentration result. So it's probably better just to fix t equals 1 and see what happens when the number of data points n goes to infinity. And so the one other question, I think I'll go over this very quickly here. Can we compute the moments of rho n like Philip Ernst did for rho in his paper in 2017? And maybe more importantly, at what speed do the moments of rho n or rho n itself converge to rho? In what sense? Could this convergence be the basis for a test of independence of the time series? And that's the main question that I have in the title of this presentation. And then, so here we're going to go through a couple of pictures here. Why are these questions important in practice? I think I've already explained how this could be important in the case of rejecting a hypothesis that two time series are independent, which would be a big mistake if those time series are accumulations of data. So for instance, if you're looking at, in a case, I'm not saying this is a true question which is unresolved, but just to explain, when you're looking at time series data for environmental statistics, the time series data for concentrations of CO2 in the atmosphere, especially since the beginning of the Industrial Revolution in 1850, that's an accumulation, right? We keep pumping more CO2 into the atmosphere, and the time series that you look at of CO2 concentration or greenhouse gas concentrations is a random walk in some sense, right? And then you might ask yourself, well, is the same thing happening with the time series which represents the global average the global mean surface temperatures of planet Earth over the same period? Well, the global surface temperatures of planet Earth over the period from, let's say, 1000 until 1850 might have looked more like an Ornstein-Uhlenbeck process, but since 1850, it's been kind of following CO2 concentration. And so it itself might actually be, even though it's not true in reality that it's an accumulation of things, it responds to CO2, and so it's going to look just like a random walk itself. And so if you take those two time series from 1850 until today, even at a yearly resolution, you're going to have two non-stationary time series. You're going to see whether they're correlated, and you're going to say that, yes, clearly the number of rho that you get with these two particular time series which have 150 data points in them, we're getting a number rho which is very far from 0. And then voila, we now have proved that, or at least there's this very strong association between the fact that CO2 has been increasing since 1850 and the global average temperatures have been increasing since 1850. Well, there's not a lot of debate whether this is true or not. Raise your hand if anybody here is a climate denier. All right, so I work in Texas, but I live in Michigan, and in the county where I live in Michigan, there's lots of climate deniers, and we have all sorts of interesting conversations every day. It's interesting. But I'm not a climate denier, even though I work with climate scientists who tell me that we should be talking about natural climate variability, and they're very smart. to say that. But in this particular case, you can see that when we do this calculation of this correlation, we're falling exactly in the trap of Yule's nonsense correlation of trying to correlate two non-stationary time series, seeing that the result is non-zero, declaring victory, when this is exactly what Yule told us not to do. Make sense, folks? So this is exactly what's happening. And there's another context in which something also just as stupid as this actually happened in climate change attribution. And I just wanted to show you guys a picture real quick. This is a graph. You don't have to pay attention to what this graph is, but I'll just tell you real quick. This is a graph from a paper that came out a couple of months ago in the Journal of Climate. I helped with this paper. The lead author is Julien Emigé, who's a climate scientist from University of Southern California in Los Angeles. And these are reconstructions of what happened to the temperatures of climate Earth, depending on various types of models, using what we call proxy data. You've probably heard of proxy data. Y'all know about tree rings and ice cores and a tree ring, yeah. When you take a tree that's 1,000 years old and you pull a core out of the tree, you can count how many rings there are, and that tells you how old the tree is. But if you look much more carefully, this is an actual science. You can see how wide the spacing is between each rings, and this is a very, very high fidelity reconstruction of what the temperatures were doing at the frequency of a year in the past. And so people use these types of proxies in order to predict what the temperatures were doing at that time. So use these types of proxies, tree rings. Same thing if you go to Greenland, you can pull out a core from the Greenland ice cap, and also you get a sense of what was going on with the climate. So raise your hand if you have. So I might actually skip really quick over the math in this presentation, even though I know that Renee likes the math, but we're going to skip real quick over it. Yeah. At least there's a little bit of math on this board. Have you heard of the hockey stick controversy? Anybody? This is really famous. Like, you guys are paying zero attention to climate science at all? Nobody? My apologies, folks. Like, wake up. Hockey stick controversy? The hockey stick controversy is this. Back in the late 1990s and early 2000s, there was a very famous climate scientist who's still working at Penn State, which is the best climate science lab in the US. And he said, well, when we look at the average temperatures from the year 1000 into the year 2000 and we reconstruct them, the effect that you get looks something like this, where there's a decrease. It decreases steadily. It's been decreasing steadily since 1900 until around 1850. And then from 1850, it starts increasing steadily at a very rapid pace. And there's no doubt at all that it was decreasing at a very steady pace, and now it's increasing at a very steady pace. And so for any Canadians here in the room? No? Or Russians? Yeah, okay. So you've heard of hockey, it's a sport. There's a stick, and the stick looks like this, am I right? Yeah, it's the hockey stick. And so it's not true that the
For people doing financial math, the hockey stick is the payoff of the crutch.
Yeah.
So everybody knows about hockey stick,
but there's no controversy in finance because there's no controversy in finance because, as we all know, the people who do math finance are the masters of the universe. Do we still use that term? Yeah. Okay. So in climate science, which is as important as quant finance, the hockey stick controversy is that it's not true. This picture is not a high fidelity reproduction of what really happened in history. If you look at some of the other graphs, this one's a little bit exaggerated. But there's other where you can see there's some ups and downs. There's something which was called the medieval warming period over here, and then there was a little ice age here around 1600, 1700. And so these are better representations based on these proxies. And so this is another example where famous scientists were using very, very bad statistics in order to make people, in order to get people to believe that climate change is real. So the moral of this story is that it shouldn't be necessary to use bad statistics to try to convince people about something which is actually real. Having said all this, let's maybe move on. Oh, I wanted to mention also, so this is a newspaper article. In fact, yeah, it's clear that I'm not going to get to any of the math in this presentation because I had some props here, but let me show you. So you can see that's me in the middle of the picture there, and I'm surrounded by some Nigerian farmers. We organized a workshop in northeast Nigeria in the city of Maiduguri in May in 2024, and we interviewed these farmers. They came from all around, and we wanted to ask them about their impressions of how climate change is affecting their lives. Can you see I'm taking notes on that little notebook? That's this notebook right here. So this is also real, and one of the reasons. So I'm not going to get into the details, but this is a real picture. This is a real newspaper article that appeared on February 19 this year in the Nigerian national press. And so the upshot of this particular event, this workshop that happened last year, is that Yule's nonsense correlation is also something which is going on with what people are saying is going. So maybe you've heard of the Lake Chad, which is in northeast Nigeria, northern Cameroon, eastern Chad, and southern Niger. Does that ring a bell? Le Lac Chad? Anybody? Yeah, le Lac Chad, bien sûr, évidemment. Les gens connaissent. Oui. So, enfin, quand je dis les gens, c'est vous, monsieur. So there's also controversy with Lake Chad and why it might have been drying out. It's not drying out now, and that's another problem that people don't understand. But so we were determined to try to figure some of these things out, and Yule's nonsense correlation is one of the things that we think is going on with how wrong people are getting stuff. So that's this picture. And so as a reminder of the object that we're dealing with, the object y12 that we had in the numerator of our expression for rho can be written as a second chaos object. So I'll probably just go through these slides real quick so I can get to the stat part. So this y12 is a second chaos object. You can write it a couple of different ways. In the case of Brownian motion, the kernel that you have here is explicit. And so I don't know how many people are familiar with the Wiener chaos analysis. I guess it's a sub-branch of Mathématiques calculus or analysis on Wiener space. But the interesting thing about the second Wiener chaos is that a lot more things are known in the second chaos than in other chaoses. So doubled integrals of deterministic functions with respect to one or two different Brownian motions are always second chaos objects. So that's a representation of the numerator of rho. And then you can also, and the reason for that is you can do this polarization to see what happens. For the denominator terms, they look like this. If the correlation is non-zero, you can rebuild the model in such a way that W2, this is something which is trivial, everybody knows how to do that, how to do the linear regression of W2 against W1 when there's a non-zero correlation R. And then you do some math, it's all very cute, and then you call Philip Ernst, who's the only person in the world who knows how to do the rest of this calculation. We were trying to compute the variance of rho n to see if we can get a little more information compared to his 2017 paper when the two time series that we're talking about are actually Gaussian random walks. So no calculations have been done no exact calculations have been done for the moments of rho n, except in the case where the random walks have Gaussian increments, because we developed this theory just based on the second Wiener chaos. You can't do that with any other distribution. And so, there's a method that Philip Ernst invented. It uses the trivariate moment generating function of the three objects, blah, 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 blah. It's complicated. These calculations are insane. And so, you get to the end of it and you finally find that, yes, we are capable of computing the moments of rho n. But that leaves another question. So this is the main result of a paper that appeared in SPA maybe last year. And in the same paper, we asked this easier question, which is actually much more important in practical terms. So this one is maybe one to pay attention to. You look at the first moment of rho n, because you're in this case, we're looking at the time series which is used for rho n is Gaussian increments. Rho and rho n can actually be coupled in the same probability space. So unlike in the general case where we just have the convergence distribution, in this case we have convergence in L1 or in L2 in every LP because they're members of, you can do this in every LP because of the way things are set up. So there's a coupling argument here. And that gives us a very clear way to find an upper bound of the Wasserstein distance between the law of rho n and the law of rho. So this is just from general theory, because there's a coupling between those two sequences, the one with discrete time, the one with continuous time. There's some calculations that have to be done here in order to do things well, more insane math. One of the things that is completely unnecessary is that you can compute for the numerator and for the denominator terms in the rho and the rho n, you can compute the second moments exactly. So this is kind of astounding. It's completely unnecessary. All you would need to do is to put a little o, 1 over n6 if you wanted to, and that would be sufficient to get the results that are of interest to figure out speeds of convergence. But you can also do it exactly, because why can you do it exactly? Well, I don't know. All I know is I have to ask Philip Ernst how to do it, and he does it. Yeah. So, and so the answer that we get is the Wasserstein distance converges to 0 at this speed. I want to remind you, so that's an interesting result, the quantitative result on the rate of convergence of rho n to rho. I want to remind you that the Wasserstein distance is controlled by the first moment. It's controlled by, so we're actually talking about an upper bound on the first moment of rho n minus rho. And again, the upper bound is of order 1 over n. You see you have a concentration result here. If you multiply rho n minus rho by n, this should have a diffuse behavior, just like in the CLT where you multiply by square root of n. But here, you don't multiply by square root. It's n itself. There is a concentration result happening, but it's much faster than the CLT. And as a matter of fact, it turns out to be of CLT type, but it's not of the same scale. It's much faster. And so here's, in fact, you can also compute, this expression here. You can see it's 1 over n squared. I've multiplied by n over here. You get a 1 over n squared as a second term. So there is concentration. There's a diffuse behavior at the level of this random variable when you multiply by n. And then, so we can skip all this. Well, what do I have, like 5 minutes left? That's it? Yeah, okay. Let me see. Let me try to explain maybe what the key point is. So there's a theorem so these random variables here are in the second Wiener chaos, and there's a theorem by Yvan Jourdain and Guillaume Pauly that came out in EJP in 2012. I don't know if y'all remember the structure of the possible limits in law of sequences in the second Wiener chaos. Does anybody heard of this result? Like I remember, I was friends. I'm still friends, I guess, with Yvan. We haven't seen each other in a while, but I remember at the time I was very impressed. Yvan Jourdain, everybody heard of Yvan Jourdain? Maybe yes, probably. Okay. So he and Guillaume Pauly proved that when you have a sequence of random variables in the second Wiener chaos, the only possible limits in distribution that you get out of a sequence in the second Wiener chaos, there's only one possibility. It's all the convolutions of Gaussian limits. You have a Gaussian distribution, you have a second chaos distribution, you can convolve the two, and that gives you all the possible limits in law of a sequence in the second Wiener chaos. And it's a general theorem, it works for everything, it's not quantitative, but what we proved, and let me maybe skip forward a little bit, we proved that we have something much more specific. So y12 is the same thing that we've been talking about. y12n is an. You also have this y11, this y22, and we call them a, b, and c. And the object that we're after is equal to, so this rho is equal to this function f, this very simple function up here, this ratio of the vector u. The vector u is a, b, c, or a, n, b, n, c, n. And so the question is, so this is literally the same rho I've been talking about. This is the same rho n I've been talking about. This function f is just this deterministic function over here. U is trivariate, un is trivariate, and u minus un multiplied by n has a diffuse behavior. And we know from Guillaume Pauly and Yvan Jourdain that the diffuse behavior has to be either Gaussian or second chaos or a convolution of the two. Well, this is what actually happens. It is a convolution of the two. There exists a limit of n times rho n minus rho. It can be written as the sum of two terms. A vector v, which is the vector v is the one which is written over on this side. If you look at it, and so here I'm going to wave over at the technician at the back so that he can maybe pan over to this board over here if you can see me. Well, maybe not, but so there's an expression here on the board which shows the exact formula for the v which is on the slide. Now we can come back to the slide. We don't need that board anymore because we've seen it on the screen. We can come back to the slide, and so you'll see that on the slide, v is a sum of several things here, and each one of them is in the second Wiener chaos. You can compute the expectations of all these terms. They're all equal to 0. Each of them is a product of normals, and so you're in the second Wiener chaos here. So v is a second Wiener chaos term, but it depends explicitly on W1 and W2. It depends explicitly on W1 and 2. So it's actually something which is observable given the data that you have. That's v. And then there's another term also which is part of the limit of n rho n minus rho, which is Gaussian with a covariance Gaussian independent of W1 and W2, actually conditionally dependent because the covariance structure of that Gaussian terms is a covariance matrix. I'm not going to pan over to that one because I didn't finish the formula, but there's a 3x3 covariance matrix over here, which is conditionally, so the Gaussian limit, the Gaussian part of the limit of n rho n minus rho is conditionally Gaussian given W1 and W2. So when we're talking about what type of limit do we have, one of them is observable second chaos. The other one is Gaussian with a covariance function which has a formula similar to the one that was on this board. That formula it looks like second chaos. When you look at the details, I don't actually have it on the board at all. When you look at the details, that conditionally Gaussian distribution is actually also in the second chaos because It's scaling arguments which give you the covariance or Gaussian objects with respect to the observation, and then this other Gaussian character which comes out of a CLT type effect, which gives you this conditional Gaussian law. Okay, so if I had spent less time telling stories about René trying to embarrass him, it didn't work, and then telling you about Northeast Nigeria, I would have time to explain why this is happening. So we have Nourdin and Poli were right. The limit is of second chaos type. There's no Gaussian component. It's a sum of two terms. They're both second chaos, but here we have an example where one of them is dependent on the original data, W1 and W2, and the other one is conditionally dependent but has a Gaussian character given the data, but it's also in the second chaos. So it's a very complex structure. We've never encountered this sort of thing before as an example. Maybe some of you have, and I'd like to hear from y'all either now or later if you have. And based on all this, so that would be kind of the end of my presentation. So based on all this, this limit here is normal with this mean, which is data dependent, with this covariance structure, which is data dependent. And so unlike, so I might actually stop on this slide and I'll just say in 1 minute, there's a couple more slides here which give the application to how to do testing for your trajectories and statistics. You can test using this particular concentration result, which is an exotic form of some sort of weird CLT where the inherent rate is n and not square root of n. It's exotic because in a normal CLT, even if you have an asymptotic variance, you know that you can compute it using the statistics of your data. Here, it's not the statistics of your data that you need, it's your actual data that you need to compute your asymptotic distribution. But given the actual data, which you obtain in the end is actually Gaussian, so you're back on your feet. You're like a cat falling out of a 20-story building, and somehow you manage to land back on your feet, where standard statistical procedures can be used in order to build these tests using, you can even do p-values if you want, God forbid, but you can even do p-values if you wanted to, because everything can be computed using the data that you have. It's quite astounding. And the rate is faster than CLT, it's twice as fast. And so we're going to have better power properties than what an ordinary CLT would do when you're trying to test things like attribution. Yeah, that's probably the punchline, except yeah, you can. So we have a result of for those of you who know statistical inference, we have a quantitative result for the power of the test under the alternative hypothesis. We have a quantitative result for the asymptotic exactness of the test under the null hypothesis. All that works great, except everything is conditional on the data, which is completely new, and the speed is faster because of this n. So it can be done. The answer to the original question on the slide was yes. And merci beaucoup, les gars.
Thank you, Frederi, for this very dynamic presentation. Any question?
Thank you. The level of energy is amazing, and you speak very fast but very distinctly.
Oh, thank you for that. I appreciate that.
Yeah, so it's a pity we don't see the density of rho. I don't know if you have it somewhere.
Ben oui, bien sûr. Attendez.
And the other question is when the correlation is not zero, so does it concentrate to the correct one?
Yes.
Yeah.
Yeah. And so the density of rho. In fact, the other person who was on the listed on the first slide, John Roberts, he actually was running some simulations in the case of fractional Brownian motion, and there's some interesting effects. We need to try to study this, at least empirically, with respect to the Hurst parameter. But when the Hurst parameter is equal to 1/2, and so your thing is bounded between -1 and 1, and the distribution actually looks kind of like what's the semicircle law? It's not the semicircle law at all, but it looks a lot like it. And then depending on, so if you want to use a different h, then you start getting some tails, so this is convex, but you're concave, but you can get some convexity depending on h. So there's all sorts of weird stuff going on, but it's very, very diffuse. Pardon me?
For the Brownian, for a half?
For half, this is for 1/2. Yeah. So this is for h equals 1/2. And if you look at the original paper by Yule, he already had this picture. Yeah.
With many coin tosses.
With coin tosses by hand, yeah. It appeared in Annals of Statistics. No, actually, Annals of, what was it called back in 1926? Annals of Mathematical Statistics, yeah. Mathematical Statistics, yeah.
Okay, thank you.
So the thesis I signed for you was on the intermittency of the Anderson model and the Lyapunov exponent. If you did something else, I don't know who it would. So are the results on this correlation in case you're not sure that the data is Gaussian?
Oh, well, that would be wonderful. So so what I think we're going to lose is the quantitative aspect of. So beyond what I've presented here, you can also look at the rate of convergence in this new form of CLT. You can do all that in the Gaussian case. If you're not in a Gaussian case, I believe that the rate n is going to remain. No matter what kind of random walk you're going to use, you're going to still get that rate n. So when you compute the second moment of n times rho n minus rho, I believe we haven't done it, but because it's hard enough to do this. But when you compute the variance of n rho n minus rho, we can show that this is bounded. We'll be able to show that there's a limit no matter what type of increment you have for your random walk. So the answer is going to be, of course, yes, it's not a problem. You can use any random walk you want. The proof might be harder because you can't use
Yeah, but you will not be in the second chaos anymore. Am I correct?
You won't be in the second chaos, so the reason that this works is that, so when you're proving a CLT, what happens is there's a Gaussian object that comes out of nowhere, out of some alternate universe. You don't need the data that you have in front of you in order to determine what the Gaussian distribution is. There's going to be an independence, like if you think of it in terms of what kinds of objects you're looking at, and you try to couple them on the same probability space, in the standard CLT, your Gaussian object that you get at the end is going to be independent of the data. That's how the standard CLT works. And it's a little hard to explain, but in this particular case, it's not independent of the data. And so an answer like this, where at least we can find out what that mean value is, that I'm not sure that we can actually find a nice formula, although I suspect that it's probably not very different from this. So there'll be some sort of formula which involves the regular data at the level when the observation points are fixed. But when you let n tend to infinity, every one of your random walks will always have a Brownian limit. So yes, that will always work. This will always be the limit. So this is just conjecture. But you have your two random walks. They have completely arbitrary increments, but they both because the Donsker's theorem works for every random walk. So they will both converge to two separate Brownian motions, and you're always going to get this formula. Yeah.
Okay.
Not written yet, but yes, thank you. That's a very good question. Of course, we're thinking about it, and we have not had a chance to work on it yet. Thank you, Professor.
Let's thank again Frederi.